Hello everyone, let's take a look at our next problem. Let S be the sum of all numbers of the form A over B, where A and B are relatively prime, positive divisors of 1000. What is the greatest integer that does not exceed S over 10? Okay, the sum of all numbers of the form A over B, where A and B are relatively prime. Okay, so there aren't that many divisors of the number 1000, I don't think, right? 1000 is 10 times 10 times 10. So that's 5 cubed times 2 cubed. So we should be able to figure out exactly how many divisors there are. And in fact, the fact that A and B are relatively prime, and we know that A and B themselves are all going to be factors of, or they're all going to be multiples of 5 and 2 in various combinations. But I suppose if they're relatively prime, A can only have factors of 2, and B can only have factors of 5, or vice versa. So I wonder if we'll be able to just list out all the possible rational numbers A over B that satisfy this property and then just add them up. So that's going to be the first approach that I take. I don't know for sure if that'll lead to the answer, but I think it's feasible, certainly, to just list out all the possible numbers that will work. Maybe it'll be a little bit too much, but that's what I'm going to start with and see what happens. Okay, so let me talk a little bit about what I'm doing here. I have, in fact, listed what I think are all the possible combinations of A and B here. So in the first section up here, A lists through all of the powers of 5 between 0 and 3, and B lists through all the powers of 2 between 0 and 3. So these are all the possible combinations with powers of 5 in the numerator, powers of 2 in the denominator. And then I've done the same thing here, but interchanging the roles with powers of 2 in the numerator. We have to be careful not to double count the pair 1, 1. And then when adding all of these numbers up, something I noticed, which will be pretty convenient, if we think about when there's powers of 2 in the denominator, well, this here, that's going to be the sum of these 4 numbers here. But then when we change the numerator to the first power of 5, that is 5 to the 1, and we're adding up these 4 numbers, it's the same. The sum is going to be the same as this, just multiplied by 5. So when I have these empty parentheses here, they're just going to be replaced with that sum. And then when I do the same thing with powers of 5 in the denominator, powers of 2 in the numerator, there's the sums of the reciprocals of powers of 5. And then when the numerator becomes 2, this term in parentheses is the same as this one here. So at this point, what I'm going to do is I'm going to add up these 4 numbers and then replace whatever that result is in all of these parentheses here. I'll do the same thing here and replace these empty parentheses with whatever that result is. I'll add all these things up. Excuse me. I'll add all these things up, but then we have to be careful to subtract 1 from the final result and see what we get. So this here is the value of S, right? This is the sum of all the numbers with the properties listed that have powers of 5 in the denominator. This is the sum of all the numbers that have powers 2 in the denominator, and we're subtracting 1 because of the double counting. So I'll just work out what this number S is equal to, and then divide S by 10 and round down and see what we get. Okay, so I think the answer is going to be 31. There's a lot of arithmetic towards the end of this problem, more than I expected there to be. Just multiplying, dividing, adding things together. I went through it a little bit quickly, so it's possible I made some little mix-up. But I end up with, eventually, the value of s, the sum of all these numbers, is equal to this. When I work out the long division, 15,711 divided by 50, I get 314 plus the remainder, 11 over 50. Or remainder 11, so of course, the non-integer part of this ratio is 11 over 50. When I divide this by 10, I end up getting 31 plus some amount which is less than 1. I would want to go back and check my work here if I were, if this were a significant life-dependent question or something like that. But I think my approach here was more or less correct. Understanding first that the factorization of 1,000 is pretty straightforward. It's just made up of prime factors of 2s and 5s. So relatively prime pairs kind of have to have only 2s or only 5s. And then writing out all the possible combinations like this, writing out the sum and identifying that this common factor appears many places and this common factor appears many places, reduces the number of computations by quite a bit. So assuming I did the arithmetic correctly, I'm pretty sure I've got the final answer here. If I have any more thoughts or if I find some kind of errors, I'll write something in the description below. Otherwise, thanks for watching. All right, so I've realized I do actually have a mistake in this problem. The way that I have, dictated which possible fractions are admissible in this sum isn't quite right. So we have that the number of 1,000 is equal to 2 to the 3 times 5 to the 3. And what I said is that each of these rational numbers, a over b, has to be equal to 2 to the m divided by 5 to the m, or 5 to the m over 2 to the n, where m and n are both non-negative. But that's not actually quite right. So for example, we could allow a to be equal to 10 and b to be equal to 1. A and b are relatively prime here. But this pair of a and b doesn't fall into either of these two arrangements. The thing that I sort of mixed up, and what I'm going to do is I kind of go through this problem again right now, is realize that all of the fractions I'm allowed to have basically cannot have a 2 in both the numerator and denominator, or a 5 in both the numerator and denominator. So what I'd been doing before is I said the numerator has to be all 2s and the denominator all 5s, or vice versa, but that you can actually mix them up between the numerator and denominator, but all of these prime factors of 2 and 5 can only appear in one of either the numerator or denominator. So the sum we actually want to compute here, we want to look for, so first we have numbers that look like a over b, where, actually the way I'll write this is 2 to the n times 5 to the m, where both n and m, sorry, not between 0, they're between -3 and 3. Okay, so what this does is, if I have a number like this, how do I say this? If I think about this, fraction, a factor of 2 cannot appear in both the numerator and denominator. The same thing goes for 5. A factor of 5 cannot appear in both the numerator and denominator. And so every number which can be written like this, without a factor of 2 in both the numerator and denominator, A contains a whole bunch of factors of 2 and 5, but if it has at least 1, 2, or at least 1, 5, then B cannot have any factors of 2 and 5, 2 or 5. So all combinations of numbers like this can be written in this form where n and m are between -3 and +3. And so what I want to do is simply add up over all values of n and m the quantity like this. So we can kind of decouple the n and m, where I'm going to factor the 2 to the power of n outside, so that I have 2 to the n times the sum of the corresponding m terms. Okay, and so now I just have 2 series that I need to add up. Oh goodness, I'd have to remember the formula for, I know the formula easy for an infinite geometric series. I can never remember the formula for a finite geometric series. Okay, I'm going to spend 2 seconds just deriving this. I know this is kind of like the kind of thing that, especially for contest math, you should have this memorized. But let me go ahead and just quickly derive the formula for the sum of a finite geometric series. Okay, I've decided to cheat a little bit on this one and use a calculator for the final part of the arithmetic. The numbers ended up being quite a bit larger and unwieldy than I thought, and I didn't want to extend the length of this video, especially considering this is like a follow-up segment. This question comes from a contest where you're not supposed to have access to a calculator, but in the end, the sum divided by 10 is a little bit more than 248. So yeah, that ends up being the correct answer. What I'd done before left out a significant number of terms from the overall sum. Thanks for watching.